Hello and welcome, fellow stargazers. Before we dive into the quiet secrets of the moon, take a moment to subscribe and join us on this journey, so you never miss a chance to explore the universe calmly and curiously. Tonight, we're going to discover why the moon spins, yet always shows the same face to Earth. You'll gently follow its orbit, rotation, and subtle wobbles, learning the real science behind its motion. Let your mind relax as precise measurements, quiet observations, and natural laws guide you. Allow curiosity and calm to settle together as we begin by meeting the moon exactly as it is. Steady, measurable, and waiting to be understood. You look up at the moon and allow it to be what it truly is, a physical world moving through space, governed by measurable laws. It hangs in the sky with quiet consistency, close enough to feel familiar, yet distant enough to invite careful study. Long before telescopes or spacecraft, people noticed its repeating patterns. Today, those patterns are explained using observation, measurement, and physics rather than story or symbol. The moon is Earth's only natural satellite. Its average distance from Earth is about 384,000 kilometers, measured precisely using laser ranging experiments. This distance is not guessed or assumed. It is confirmed by sending pulses of light from Earth, reflecting them off mirrors placed on the lunar surface, and timing their return. Light travels at a known speed, allowing the distance to be calculated with extraordinary accuracy. In size, the moon is large compared to its planet. Its diameter is about 3,400 kilometers, roughly 1/4 the diameter of Earth. This makes it unusually large relative to the body it orbits. Because of this size, its gravitational influence on Earth is strong enough to shape tides, stabilize orientation, and affect long-term planetary behavior in measurable ways. The moon's mass is about 1/80th of Earth's mass. This value comes from observing how objects move under its gravity, including orbiting spacecraft and the behavior of Earth itself. Mass determines how strongly gravity pulls, and gravity determines how objects move. These relationships are not abstract. They are confirmed every time a spacecraft enters lunar orbit and follows a predictable path. You imagine the moon not as a glowing disk, but as a rocky sphere with mountains, plains, and impact scars. Its surface has been mapped in detail by orbiters, landers, and astronauts. Cameras and instruments record elevation, composition, temperature, and gravitational variation. Nothing about its physical presence is left to guesswork. Each measurement builds a clearer picture of what kind of object it is. The moon does not shine on its own. The light you see is sunlight reflected from its surface. This reflection depends on angle, texture, and composition. Darker regions reflect less light, while brighter highlands reflect more. These differences help scientists understand surface materials and geological history. Even brightness becomes a source of data. As you keep observing, the moon begins to feel steady rather than mysterious. It rises and sets because Earth rotates. Its shape changes because your viewing angle shifts as it moves along its orbit. These motions follow precise patterns that can be predicted far into the future or traced back into the past. Stability emerges from repetition, and repetition allows understanding. Gravity binds Earth and the moon together in a shared system. They do not exist separately. Both bodies orbit a common center of mass, called the barycenter, which lies inside Earth but not at its center. This shared motion is subtle but real, and it can be measured through careful tracking of Earth's position in space. The moon's orbit is slightly tilted and gently elliptical. This means its distance from Earth changes over time, and its path is not a perfect circle. These variations are small, regular, and predictable. They influence how the moon appears in the sky and how strongly it affects tides. Even small deviations matter when observed over long periods. You may notice that the moon feels emotionally constant. Night after night, it returns in familiar form. That sense of constancy arises because its motions are governed by simple, stable laws. Newton's law of gravitation and Einstein's refinements describe its behavior with remarkable precision. These equations are tested continually by observation and never require adjustment to fit lunar motion. The moon formed early in Earth's history, likely after a collision between the young Earth and a Mars-sized body. This explanation is supported by rock samples, isotopic ratios, and computer simulations. Lunar rocks closely resemble Earth's mantle, suggesting a shared origin. This history is written into the chemistry of stone. When you rest your attention on the moon, you are observing a system shaped by time. Impacts, cooling, and orbital interactions leave traces that remain visible today. Craters persist because there is no thick atmosphere to erase them. The surface becomes a record, preserving information across billions of years. The moon's lack of atmosphere shapes everything you see. Without air to scatter light or soften temperature, shadows remain sharp and extremes remain large. Daytime surface temperatures can rise far above the boiling point of water, while nighttime temperatures drop far below freezing. Instruments placed on the surface measure these swings directly, confirming models of heat transfer in airless environments. Seismic instruments left by astronauts detect subtle vibrations called moonquakes. These tremors reveal information about internal structure. Data shows a crust, mantle, and small core, though less active than Earth's. The moon is not geologically dead, only quiet. Its internal energy dissipates slowly, leaving faint but measurable signals. As you allow these facts to settle, familiarity deepens. The moon becomes a place defined by numbers, motion, and evidence. Its presence overhead feels calm because it follows rules that do not change. Gravity pulls, momentum carries, and time allows patterns to repeat. With this foundation, understanding motion no longer feels complex. It feels natural, steady, and ready to be observed with patience. From Earth, the moon appears close enough to touch, yet its true scale becomes clear through measurement. Light travel time, orbital speed, and angular size all agree, reinforcing one consistent picture. Observation supports calculation, and calculation supports understanding. You remain quietly aware that every visible detail rests on careful measurement, inviting deeper attention to how motion itself is defined and observed. The moon stays where physics places it, neither drifting nor wandering. Its reliability allows thought to slow, curiosity to soften, and attention to rest on motion that repeats, preparing your mind to notice how movement can appear still when viewed from a single place. You begin by letting motion become something precise rather than assumed. In everyday experience, movement often feels obvious. An object spins, travels, or stays still, and your senses quickly form conclusions. In astronomy, however, motion must be defined with care. Scientists rely on consistent reference points and measured change over time to describe how anything moves through space. Rotation describes an object turning around its own internal axis. This axis may be visible, like the line through Earth from pole to pole, or it may be defined mathematically. What matters is that points on the object change orientation relative to distant space. Revolution, by contrast, describes an object traveling along a path around another body. The two motions are independent. An object can rotate without revolving, revolve without rotating, or do both at the same time. You consider Earth as a familiar example. Earth rotates once approximately every 24 hours, producing day and night. At the same time, it revolves around the sun once each year. These motions are measured by tracking Earth's orientation relative to distant stars and its position along its orbital path. Neither motion is inferred from feeling alone. Both are confirmed through observation. In science, motion is never described in isolation. It is always measured relative to something else. This is called a reference frame. For objects in space, distant stars serve as stable reference points because their apparent motion is extremely slow over human timescales. By comparing an object's position or orientation against these distant markers, astronomers determine how it moves. You imagine marking a specific feature on a rotating object. If that feature changes its orientation relative to distant stars, rotation is occurring. If the object changes its position along a path around another body, revolution is occurring. These definitions are simple, but applying them requires patience and precise measurement. Confusion often arises because rotation does not always look like spinning in the everyday sense. When you watch a coin spin on a table, rotation is obvious. In space, rotation can be slow, subtle, and synchronized with other motions. An object may rotate once over many days or weeks, making the change difficult to notice without long-term tracking. The moon provides a clear case where intuition can mislead. From Earth, the same face always appears to point toward you. At first glance, this suggests no rotation at all. Yet science does not rely on first impressions. Instead, astronomers track the moon's orientation relative to distant stars, not relative to Earth alone. This distinction is essential. If you imagine following the moon from a fixed point in space far above the solar system, you would see something different. As the moon travels along its orbit, its orientation slowly changes. The same side continues to face Earth, but that requires the moon to rotate at a very specific rate. This rotation matches its orbital period exactly. You learn that motion can appear different depending on where you observe from. From Earth, the moon seems fixed in orientation. From distant space, its rotation becomes evident. Both perspectives are correct within their own reference frames. Science accounts for this by clearly stating which frame is being used. Astronomers rely on mathematics and observation to move beyond appearance. They calculate angular velocity, which describes how fast an object rotates, and orbital period, which describes how long it takes to complete one revolution. These quantities are measured independently and then compared. When they match, synchronization becomes evident. Time plays a central role in defining motion. A single snapshot reveals position but not movement. Only by comparing positions over time can motion be confirmed. This is why early astronomers kept careful records night after night, noting how celestial objects shifted against the star background. Patterns emerged slowly, revealing consistent laws. You begin to sense how careful this process must be. Science resists assumptions. It asks what changes, how quickly it changes, and relative to what. Motion becomes a sequence of measured states rather than a vague impression. This approach applies equally to planets, moons, spacecraft, and even galaxies. Rotation is detected through repeating orientation changes. Revolution is detected through repeating paths. Both rely on regularity. When patterns repeat, they can be quantified. Once quantified, they can be predicted. This predictability is what allows spacecraft to navigate and missions to succeed. You also learn that zero rotation is rare in nature. Most objects in space rotate to some degree, often as a result of how they formed. Conservation of angular momentum ensures that collapsing clouds and colliding bodies naturally acquire spin. Rotation is not an exception. It is a consequence of physical law. The moon's motion must therefore be described using the same careful language applied to all celestial bodies. Whether it appears to spin from one viewpoint or not is less important than how its orientation changes relative to a stable frame. Science chooses the frame that reveals the underlying behavior most clearly. As these definitions settle in your mind, confusion begins to fade. Motion no longer feels subjective. It becomes something that can be measured, described, and agreed upon. The moon's steady behavior fits comfortably within these definitions, even if it challenges everyday expectations. You remain gently aware that understanding motion requires patience. It asks you to watch slowly, to compare carefully, and to trust measurement over appearance. With these tools, even subtle movements reveal themselves, showing that stillness in the sky is often the result of perfectly balanced motion waiting to be observed with the right frame of reference. You settle into the idea that rotation is not something assumed, but something demonstrated. For the moon, proof comes not from a single observation, but from patterns recorded patiently over time. Astronomers look for change, not drama. They track how specific features behave relative to the wider universe, allowing motion to reveal itself slowly and reliably. One of the simplest ways to confirm rotation is by choosing a fixed reference point. For the moon, these points are surface features such as craters, mountain ranges, and dark volcanic plains. These landmarks are stable over millions of years. They do not shift or erode significantly because there is no atmosphere, flowing water, or active plate tectonics. Once identified, they serve as dependable markers. You imagine a particular crater near the moon's equator. Astronomers photograph it repeatedly, recording its orientation relative to distant stars. Over time, its angle changes in a predictable way. This change cannot be explained by revolution alone. It indicates that the moon is turning around its own axis as it travels along its orbit. Early evidence comes from telescopic observation. Long before spacecraft existed, astronomers noticed slight changes in how the moon's surface was presented. Careful drawings made over decades revealed that the orientation of surface features shifted subtly. These changes were slow, but consistent. When plotted mathematically, they matched the rate expected if the moon rotated once during each orbit around Earth. Modern confirmation comes from spacecraft tracking. Orbiters around the moon measure gravitational variations and surface alignment with extreme precision. Cameras capture the same features from slightly different angles as time passes. When these images are compared, the rotation becomes unmistakable. The moon completes one full rotation relative to distant space in about 27.3 days. This number is not arbitrary. It matches the moon's orbital period around Earth. Such equality is not coincidence. It is the defining characteristic of a tidally locked system. But before understanding why this happens, scientists first establish that it does happen. Rotation is confirmed independently of any explanation for its cause. Laser ranging experiments provide another layer of evidence. Retroreflectors placed on the moon by astronauts return laser pulses sent from Earth. By tracking the timing and orientation of these reflections over decades, scientists detect slight variations consistent with rotation and wobble. These measurements confirm not only that the moon spins, but that its spin is extremely stable. You notice that rotation can be difficult to visualize when it is synchronized. If you walk around a table while always facing the center, you are rotating even though the same side faces inward the entire time. The moon behaves in a similar way. It rotates once per orbit, keeping one hemisphere directed toward Earth, while still turning relative to the wider universe. The key is choosing the correct reference frame. When scientists observe the moon relative to Earth, rotation is hidden by synchronization. When they observe it relative to distant stars, rotation becomes clear. Both perspectives are valid, but only one reveals the full motion. Astronomers also study the moon's angular momentum. This quantity describes how much rotational motion an object possesses. Calculations based on the moon's mass, shape, and orbital behavior show that it must be rotating. A non-rotating moon would violate well-tested physical laws unless acted upon by an unknown force. No such force is observed. The moon's rotation is also confirmed through subtle effects called librations. These are small oscillations that slightly change which parts of the surface are visible from Earth. Libration would not occur if the moon did not rotate. The exact pattern of these oscillations matches predictions based on a rotating, tidally locked body. You begin to appreciate how layered scientific confirmation is. No single measurement stands alone. Telescopic records, spacecraft imaging, laser data, and mathematical modeling all converge on the same conclusion. The moon rotates. It does so steadily, predictably, and in harmony with its orbit. This consistency matters. Science gains confidence not from novelty, but from agreement across methods. When independent techniques lead to the same result, understanding deepens. The moon's rotation is one of the most thoroughly confirmed motions in astronomy because it can be tested in so many ways. You also notice how human perception differs from measurement. Your eyes see the same face of the moon night after night. Instruments see gradual change. Neither is wrong. They simply operate on different scales. Science extends perception by allowing time to accumulate and detail to emerge. Rotation, in this context, becomes a quiet fact. It does not announce itself with obvious spinning. It reveals itself through patience. The moon turns at a rate that feels slow only because human attention is brief. When time is allowed to stretch, motion becomes undeniable. You rest with the idea that even when something seems still, it may be moving with great regularity. The moon's spin is not dramatic, but it is exact. Its axis remains stable, its period consistent, its behavior aligned with physical law. Understanding this does not disturb the calm view of the night sky. It deepens it. As your awareness settles, the moon remains overhead, unchanged in appearance yet rich in motion. Its steady rotation continues without pause, shaped by gravity and time, inviting a deeper look at the forces that bring spinning and orbit into perfect balance. You allow gravity to become more than an abstract idea. It is not just the force that keeps feet on the ground or guides planets along their paths. Gravity also acts unevenly across objects, creating measurable differences in force from one side to the other. These differences are called tidal forces, and they play a quiet but decisive role in shaping long-term motion. When one body orbits another, the side facing its partner feels a slightly stronger gravitational pull than the side facing away. This difference may be small, but it is real and detectable. Over time, it stretches the object very slightly along the line connecting the two bodies. Even solid rock responds to this force, deforming by tiny amounts that can be measured indirectly. You imagine Earth's oceans rising and falling under the moon's influence. Those tides are the most visible example of tidal forces at work. But the same forces act on solid ground as well. Earth's crust flexes by centimeters each day due to lunar gravity. Instruments confirm this subtle motion. The moon experiences similar effects from Earth's stronger gravitational pull. As the moon orbits Earth, tidal forces distort its shape slightly, creating a small bulge. If the moon rotated at a different rate than its orbit, this bulge would not remain perfectly aligned with Earth. Instead, it would be carried ahead or behind by rotation. Gravity would then pull on this misaligned bulge, creating a torque that changes the moon's spin. Torque is a force that alters rotational motion. In this case, it acts to slow or speed rotation until alignment is achieved. Over long periods of time, this process removes rotational energy and converts it into heat within the moon's interior. That heat is minimal today, but over millions of years, the effect accumulates. You begin to see tidal locking as a natural outcome rather than a special condition. As long as energy is lost through internal friction, rotation will gradually adjust. The most stable state is one where the same side always faces the source of gravity. In that state, the tidal bulge remains aligned, torque disappears, and energy loss slows dramatically. This process does not require intention or guidance. It follows directly from physical law. Given enough time, many orbiting bodies evolve toward this configuration. The timescale depends on distance, mass, internal structure, and initial rotation rate. For the moon, calculations show that tidal locking would occur relatively early in its history. Evidence supporting this comes from computer models tested against observation. When scientists simulate the early Earth-Moon system using known physical properties, tidal locking emerges consistently. These models match the current orbital distance, rotation rate, and angular momentum distribution measured today. You notice that tidal locking does not stop rotation entirely. The moon still rotates once per orbit. What changes is the relationship between rotation and revolution. Synchronization replaces mismatch. Motion remains, but it becomes balanced. Other examples help confirm this understanding. Many of Jupiter's and Saturn's large moons are tidally locked to their planets. Spacecraft observations confirm that the same hemisphere always faces the parent planet. Their rotation periods match their orbital periods precisely, just like the moon's. Even beyond the solar system, tidal locking is expected. Many exoplanets orbit very close to their stars. Models predict that these worlds should become tidally locked within relatively short astronomical timescales. Observational evidence, such as consistent thermal patterns, supports this prediction. You return attention to the moon and recognize that its current behavior represents a state of minimum energy. Systems naturally evolve toward such states when energy can be lost. Friction inside rock, though weak, is enough over vast spans of time. The moon's interior absorbs and dissipates energy slowly but persistently. This understanding helps explain why the moon's rotation is so stable today. Once locked, little remains to change it. Without large external disturbances, the system stays in equilibrium. Small variations still occur, but the overall configuration remains intact. You also become aware that tidal locking affects both bodies involved. As the moon loses rotational energy, Earth gains a small amount of orbital energy. This transfer causes the moon to slowly move away from Earth. Laser measurements confirm that the moon recedes by about 3.8 centimeters per year. This rate matches predictions based on tidal theory. Earth's rotation slows slightly as well. Days lengthen by milliseconds over centuries. Ancient geological records, such as growth rings in fossil corals, confirm this gradual change. These independent lines of evidence strengthen confidence in the underlying physics. Tidal locking, then, is not a one-time event but part of an ongoing exchange. Energy and angular momentum shift between bodies, reshaping motion gradually. The moon's locked state is a snapshot within this long process. You sense how gentle this mechanism is. Nothing sudden occurs. No dramatic moment marks the transition. Instead, rotation slows fraction by fraction until alignment is reached. Time smooths everything. What feels permanent is simply what has settled into balance. As gravity continues its quiet work, motion organizes itself into patterns that endure. The moon's steady orientation becomes a natural outcome of energy-seeking stability, preparing your attention to consider how long this process takes and what traces it leaves behind. You allow time to stretch beyond immediate experience. In astronomy, change rarely happens quickly. Processes unfold over spans that far exceed human lifetimes, yet they leave traces that can be measured with care. The moon's journey toward tidal locking is one such process, slow and steady, guided by physics and recorded in subtle evidence. When the moon first formed, it did not move as it does now. Models suggest that it began much closer to Earth, orbiting at a fraction of its current distance. At that time, Earth's gravitational pull was stronger, and tidal forces were more intense. These early conditions set the pace for how quickly the moon's rotation changed. Scientists estimate the timing of tidal locking by combining physical laws with observational constraints. They begin with known quantities: the moon's mass, radius, composition, and present rotation rate. They then apply equations describing how tidal forces dissipate energy inside solid bodies. These equations are tested using laboratory experiments on rock behavior and confirmed by observations of other moons. You imagine the young moon rotating more rapidly than it does today. Each rotation caused internal deformation as Earth's gravity pulled unevenly across its body. This deformation generated friction within the moon's interior. Friction converted mechanical energy into heat, slowly reducing the moon's rotational speed. The process repeated endlessly, rotation after rotation. The rate of this energy loss depended on how rigid or flexible the moon's interior was. Evidence from seismic data and rock samples shows that the moon cooled and solidified relatively quickly, becoming mostly rigid early in its history. Even so, slight flexing remained possible, allowing tidal dissipation to continue. Computer simulations allow scientists to explore these conditions quantitatively. By adjusting initial rotation rates, orbital distances, and material properties, researchers model how long it would take for synchronization to occur. Across a wide range of realistic inputs, tidal locking consistently emerges within tens of millions of years. This timescale aligns with geological evidence. Lunar surface features show that major volcanic activity occurred early, when internal heat was higher. As tidal energy dissipated and rotation slowed, internal heating decreased. The moon's geological quieting matches the period when tidal locking would have been completed. You notice that no single rock announces the moment of synchronization. Instead, multiple lines of evidence converge. Orbital mechanics, thermal evolution, and surface history all point toward early locking. Science relies on this convergence rather than on direct observation of past events. The moon's current distance from Earth also provides clues. As tidal locking progressed, angular momentum was transferred from Earth's rotation to the moon's orbit. This caused the moon to move outward. By measuring the present recession rate and modeling past conditions, scientists reconstruct earlier orbital distances. These reconstructions fit neatly with the locking timeline. Earth's own history supports this picture. Geological records indicate that days were much shorter billions of years ago. Fossil growth patterns reveal more daily cycles per year, confirming faster rotation. This faster rotation would have enhanced tidal effects, accelerating the moon's evolution towards synchronization. You begin to appreciate how time leaves fingerprints rather than timestamps. Nothing labels itself with an age. Instead, physical states imply histories. The moon's locked rotation implies a long period of energy loss. Its orbital distance implies angular momentum transfer. Together, they form a consistent narrative shaped by measurement. Even uncertainties are handled carefully. Scientists acknowledge ranges rather than exact dates. Locking likely occurred within the first 100 million years, possibly much sooner. What matters is not the precise year, but the scale and inevitability of the process under known physical laws. The moon's interior structure plays a quiet role in this story. A small, partially molten core would have enhanced early tidal dissipation. Magnetic evidence preserved in lunar rocks suggests such a core existed early on. As it cooled, dissipation decreased, allowing the system to settle into long-term stability. You rest with the idea that stability often requires time. Rapid change gives way to balance only after energy has been redistributed. The moon's current behavior is not a starting point, but a result. This calm rotation reflects a long past of gradual adjustment. Even now, the process has not fully stopped. The moon continues to recede, and Earth's rotation continues to slow. Changes are small but measurable. Time remains active, shaping motion quietly in the background. As awareness softens, the moon feels less like a static companion and more like a participant in a shared history with Earth. Its present stillness carries the imprint of deep time, inviting attention to how its surface and orientation preserve records of that long evolution. You let language slow and settle because in science, words matter. When describing the moon, precision replaces habit. One of the most common misunderstandings comes from naming. The phrases near side and far side are not poetic choices. They are exact descriptions rooted in motion and perspective. The near side of the moon is the hemisphere that generally faces Earth. Because the moon is tidally locked, this same side remains oriented toward Earth as both bodies move through space. The far side is the hemisphere that generally faces away from Earth. These terms describe orientation, not illumination. They say nothing about light or darkness. Sunlight reaches every part of the moon during each lunar orbit. As the moon travels around Earth, the sun illuminates different regions in turn. The far side receives just as much sunlight as the near side over the course of a lunar month. This fact is confirmed by orbital data, thermal measurements, and direct imaging from spacecraft. You may notice that the phrase dark side appears often in casual conversation. In scientific contexts, it is avoided because it implies permanent darkness which does not exist. No region of the moon is hidden from the sun indefinitely. The misunderstanding arises because one side is hidden from Earth's view, not from light itself. You imagine the moon floating in space, half illuminated by the sun at any moment. This half is not fixed to one hemisphere. It shifts continuously as the moon moves along its orbit. When you see a crescent moon, most of the near side is in darkness while a portion of the far side is fully lit. Geometry, not mystery, determines this pattern. Spacecraft provide direct confirmation. The first images of the moon's far side were returned by the Soviet Luna 3 mission in 1959. Since then, orbiters from multiple space agencies have mapped the entire lunar surface in detail. High-resolution photographs show craters, mountains, and plains on both hemispheres, all clearly shaped by sunlight and shadow. You notice that the far side looks different from the near side. This difference does not come from lighting conditions. It comes from geological history. The near side contains large, dark basaltic plains called maria, formed by ancient volcanic eruptions. The far side has far fewer maria and is dominated by heavily cratered highlands. Scientists investigate these differences using gravity measurements, rock samples, and computer models. Data shows that the lunar crust is thicker on the far side. This thicker crust made it more difficult for magma to reach the surface there, limiting volcanic flooding. On the near side, thinner crust allowed lava to spread, forming wide plains. Heat distribution also played a role. Early in the moon's history, radioactive elements were unevenly distributed within its interior. These elements produced heat as they decayed. The near side retained more internal heat, supporting volcanic activity. The far side cooled more quickly, preserving older surface features. You recognize that none of this requires speculation. Gravity mapping missions detect variations in mass beneath the surface. These variations correlate with crust thickness. Lunar samples collected from the near side confirm volcanic composition. Although no samples have yet been returned from the far side, orbital spectroscopy provides strong evidence of different mineral distributions. The moon's far side is not hidden by darkness, but by geometry. From Earth's surface, the moon's synchronized rotation keeps one hemisphere facing away. Only spacecraft that orbit the moon or travel beyond Earth's line of sight can observe it directly. This limitation is observational, not physical. Communication experiments further confirm this orientation. Signals transmitted from Earth cannot reach the far side directly. Satellites placed in special orbits relay data between far-side landers and Earth. These missions operate successfully, demonstrating the consistent geometry of the moon's orientation. You begin to feel how careful naming supports understanding. Near side and far side describe relationships that can be measured and predicted. They avoid misleading imagery. Science favors such clarity because it allows knowledge to build without confusion. Thermal measurements reinforce this clarity. Infrared instruments show that both hemispheres heat up during lunar day and cool down during lunar night. Temperature cycles match solar exposure, not Earth-facing orientation. The far side experiences the same extremes as the near side. Even eclipses reflect this geometry. During a lunar eclipse, Earth's shadow falls across the moon, darkening portions of both hemispheres depending on alignment. The event reveals that illumination depends on relative positions, not on fixed sides. As your attention rests on these facts, the moon becomes more complete. No part of it is hidden from physics. No region exists beyond explanation. Differences arise from formation and structure, not from permanent concealment. You remain aware that perspective shapes perception. From Earth, the moon presents a familiar face. From space, it is a rotating sphere bathed in sunlight from all angles over time. Science steps outside a single viewpoint to understand the whole. With language clarified and misconceptions eased, the moon feels simpler rather than diminished. Its two hemispheres follow the same laws, receive the same light, and share the same history shaped by gravity and heat. Surface differences quietly record internal processes, inviting a closer look at why one side bears smoother planes while the other holds deeper scars. You rest your attention on the moon's surface and notice that it is not uniform. Even without magnification, differences are visible. Darker regions spread broadly across one hemisphere, while the opposite side appears brighter and more heavily textured. These contrasts are not superficial. They are records, preserved carefully by a world that changes very slowly. The dark regions visible from Earth are called maria. They are large plains of solidified basalt, formed when molten rock flowed across the surface billions of years ago. These flows filled low-lying areas and cooled into smooth expanses. Their darker color comes from iron-rich minerals that reflect less sunlight than the surrounding highlands. The far side of the moon contains far fewer maria. Instead, it is dominated by lighter-colored highlands, densely covered with craters. This difference is immediately apparent in spacecraft images. The reason lies not in chance, but in the moon's internal structure and early thermal history. One of the most important factors is crust thickness. Gravity mapping missions reveal that the lunar crust is significantly thicker on the far side than on the near side. These measurements are made by tracking how spacecraft accelerate slightly as they pass over regions of different mass. Variations in gravitational pull reveal what lies beneath the surface. A thicker crust acts as a barrier. When large impacts occurred early in lunar history, they fractured the crust on both sides. On the near side, thinner crust allowed magma from the mantle to rise through these fractures and flood the surface. On the far side, thicker crust resisted penetration, limiting volcanic activity. You imagine molten rock rising slowly through fractures created by ancient impacts. Where the crust is thin, the rock reaches the surface and spreads. Where the crust is thick, the rock cools and solidifies below, never emerging. Over time, this difference shapes the visible surface. Heat distribution reinforces this pattern. Early in the moon's history, radioactive elements such as uranium, thorium, and potassium were unevenly concentrated. These elements produce heat as they decay. Orbital spectroscopy shows higher concentrations on the near side, particularly within regions rich in Maria. This additional heat kept the near side's mantle partially molten for longer. Extended melting allowed volcanic eruptions to continue after large impacts occurred. On the far side, lower concentrations of heat-producing elements led to faster cooling. Once the interior cooled, magma became too stiff to flow upward. You begin to see how surface appearance reflects interior conditions. The moon's exterior is not decorative. It is diagnostic. Crater density, smooth plains, and elevation all point to physical processes operating deep below. Crater counts provide another layer of evidence. Regions with many craters are generally older because they have been exposed to impacts for longer periods without resurfacing. The far side's dense cratering indicates that its surface has remained largely unchanged for billions of years. The near side's Maria are younger, having erased older craters beneath lava flows. Dating lunar samples confirms this timeline. Rocks collected from Maria solidified between about 3 and 4 billion years ago. Highland rocks are older, some exceeding 4 billion years. Although samples come only from the near side, crater statistics allow scientists to extend these age estimates globally. The moon's orientation also plays a role. Because one hemisphere always faces Earth, it has been more accessible to direct sampling and observation. However, spacecraft orbiters remove this bias by mapping both sides uniformly. Data from these missions confirms that surface differences are real and extensive, not observational artifacts. You notice that gravity itself varies across the moon. Beneath some Maria lie dense regions called mascons, short for mass concentrations. These are thought to form when dense basalt fills impact basins. Mascons affect spacecraft orbits, further confirming the link between surface features and internal structure. The far side contains fewer mascons because it contains fewer Maria. This consistency strengthens the explanation. Independent measurements align, each supporting the same underlying cause. Impacts shape both hemispheres, but their outcomes differ. Large collisions create basins everywhere. What happens afterward depends on internal conditions. On the near side, impacts are followed by volcanic flooding. On the far side, basins remain exposed and cratered. You begin to appreciate how the moon preserves contrast. Earth's surface is reshaped constantly by water, wind, and tectonics. The moon lacks these processes. Once formed, features persist. Differences that arise early remain visible far into the future. Nothing about this asymmetry requires mystery. Physics provides sufficient explanation.
Gravity gouverne crust formation.
Heat governs melting. Time governs exposure. The moon's two faces are not opposites in nature, only outcomes of slightly different starting conditions amplified over billions of years. As you hold these ideas gently, the moon's surface becomes readable. Each plane and crater fits into a larger pattern shaped by measurable forces. The visible differences invite careful observation rather than speculation. With understanding deepened, the moon feels quieter still. Its surface speaks through structure, density, and age. Subtle variations in orbit and tilt allow just a little more of this surface to be seen from Earth, revealing that even locked motion contains gentle shifts waiting to be noticed. You notice that the moon does not appear perfectly fixed as it moves through the night sky. Its orientation wobbles gently, allowing glimpses beyond the hemisphere that faces Earth most directly. These slow, predictable shifts are called librations. They are measurable, calculable, and observable across centuries. Librations provide a subtle reminder that even synchronized rotation is dynamic, not absolutely static. Librations arise from several factors. One of the simplest is orbital eccentricity. The moon's path around Earth is not a perfect circle. It is slightly elliptical. Because orbital speed varies with distance from Earth, the moon moves faster when it is closer and slower when it is farther away. Its rotation, however, remains constant. The result is a small oscillation in apparent orientation, called longitudinal libration. You imagine observing the moon over consecutive nights. Craters near the edge of the near side shift slightly forward and backward. Over time, you see small portions of the far side peak around the limb. This motion is subtle but consistent. The angles involved are only a few degrees, yet over the course of a month, they reveal additional surface detail beyond the hemisphere that remains mostly Earth-facing. Tilt of the moon's axis adds another component, called latitudinal libration. The moon's rotational axis is inclined by about 6.5 degrees relative to the plane of its orbit. This slight tilt means that, from Earth, you alternately see slightly over the moon's north pole and slightly below its south pole. The effect is small, but it further expands the visible surface area. Combined, these oscillations allow observers to see about 59% of the lunar surface over time, rather than the 50% suggested by a static model. The visible extension is gradual and repeated each orbit. Photographs taken night after night document this gentle revealing of surface features. Diurnal libration provides a third minor effect. It occurs because observers on Earth are not in a single, fixed position. As Earth rotates, different points on the planet view the moon from slightly different angles. This daily rotation causes a very small apparent shift in the moon's orientation. For careful observers, it is measurable and contributes to the overall libration. You imagine measuring these oscillations precisely. Modern astronomy uses telescopes and spacecraft tracking to quantify librations to fractions of a degree. Historical records, including detailed drawings by astronomers over centuries, also capture these subtle motions. Observations consistently confirm predictions based on orbital mechanics and rotation rates. The cause of longitudinal libration is fully explained by Newtonian mechanics. Kepler's laws describe orbital motion, and the moon's rotation is nearly uniform. Slight mismatches between rotational speed and orbital velocity produce a regular oscillation. This predictable wobble aligns exactly with the moon's position along its elliptical path. Latitudinal libration follows from simple geometry. The moon's inclined axis tilts the visible poles toward and away from Earth. Spacecraft mapping confirms the maximum angle and surface regions revealed. Combining this with orbital data, scientists can reconstruct the exact extent of the far side that becomes visible over time. Diurnal libration is a straightforward consequence of perspective. Different points on Earth are separated by thousands of kilometers. Observers at the equator view the moon from a slightly different angle than observers at higher latitudes. These small differences shift the apparent orientation of edge features. Calculations match these variations precisely. You begin to appreciate the predictability of librations. Unlike weather or tectonic motion, these shifts follow well-defined physical laws. Over a complete lunar month, every cycle repeats almost exactly. Slight perturbations exist, caused by the gravitational influence of the Sun and other planets, but these are minor and calculable. The pattern remains remarkably steady. Observational records match theoretical expectations. Using telescopes, astronomers track features near the limb of the moon and record their positions over time. The measured oscillations are consistent with calculated librations. The moon's surface thus becomes a reliable reference for testing orbital and rotational models. You notice that libration enhances the opportunity to study the moon. Features near the limb, otherwise hidden, become accessible at certain times. This allows scientists to expand mapping coverage without leaving Earth and to identify regions for potential spacecraft missions. The interplay of rotation, tilt, and orbital eccentricity creates natural windows for observation. Librations also reveal the moon's rotational stability. Because the oscillations are predictable, they confirm that the moon's spin axis and rotation period are not changing abruptly. Variations remain within expected limits, indicating that tidal locking has produced a stable equilibrium, modulated only by minor orbital interactions. You imagine how early astronomers interpreted these motions. Careful sketches of craters and mountain ranges over weeks showed the moon shifting slightly from one night to the next. They could not measure exact angles, but they noted apparent forward and backward movements. These qualitative observations anticipated later quantitative measurements. Modern spacecraft provide more detailed confirmation. Lunar orbiters use cameras and altimeters to capture images from multiple angles, reproducing the effect of libration from precise orbital paths. Data shows that the maximum longitudinal shift is roughly 7 to 8 degrees, and the maximum latitudinal shift is about 6.5 degrees. Together, these expand the apparent lunar surface in a predictable, repeatable way. The moon's motion is steady enough that future positions can be calculated with confidence. Librations are incorporated into ephemerides, tables of predicted positions used for astronomy and navigation. By accounting for oscillations, scientists know which surface features will be visible at any given time, which supports research, photography, and mission planning. You rest with the realization that libration is evidence of subtle interaction between rotation and orbit. Nothing arbitrary occurs. The moon's wobble is a natural consequence of its shape, mass distribution, orbital eccentricity, and axial tilt. Observational astronomy confirms every element. Even the tiny diurnal component matches predictions based on Earth's rotation. The moon thus becomes more than a static companion in the night sky. Its steady motion reveals hidden terrain, making the visible hemisphere slightly larger over time. This gentle movement encourages careful observation and reinforces the precision inherent in celestial mechanics. As you watch the moon and notice its slowly shifting angles, you sense that what appears fixed is actually part of a dynamic system. Its rotation, orbit, and tilt create a subtle dance, a predictable revealing of otherwise hidden surfaces. This insight sets the stage to understand how its gravitational influence reaches beyond the moon itself, shaping the behavior of the planet it accompanies. You shift attention from the moon itself to its influence on Earth. Gravity is not just a local force. It extends across space, acting over vast distances with measurable effect. The moon's pull tugs on oceans, creating tides, but it also exerts a more subtle influence on the solid body of Earth. One of the most important outcomes is the stabilization of Earth's axial tilt. Earth rotates around an axis tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt produces seasons, alternating sunlight patterns, and variations in climate over the course of a year. Without the moon, simulations suggest, Earth's tilt could fluctuate chaotically between 0 and 50 degrees over millions of years, with profound effects on climate stability. The stabilizing effect arises from gravitational torque. The moon pulls more strongly on Earth's equatorial bulge than on polar regions, generating a gentle torque that resists changes in the axis orientation. This torque does not prevent seasonal tilt entirely. Instead, it limits extreme variations, keeping axial tilt within a narrow, predictable range. Geological evidence supports this conclusion. Sedimentary layers, growth rings in ancient corals, and ice core data provide a record of Earth's historical climate. Analyses show that axial tilt has remained relatively consistent for hundreds of millions of years. These records align with models of gravitational stabilization, confirming the moon's role in maintaining order. You notice that the stabilizing effect is gradual. Earth's axis does shift slightly over time, producing long-term cycles called Milankovitch cycles. These cycles influence glacial and interglacial periods, affecting climate on scales of tens of thousands to hundreds of thousands of years. The moon does not freeze Earth's seasons. It moderates them, keeping variations predictable. Simulations help quantify this moderation. Using detailed gravitational models, scientists calculate how axial tilt responds to planetary interactions with and without a large moon. Without the moon, tilt variations become chaotic, creating extremes that would disrupt climate patterns. With the moon, oscillations remain within a stable band, producing reliable seasonal cycles. You may also consider Earth's rotation. The moon's tidal pull slowly transfers angular momentum, lengthening Earth's day over billions of years. Geological evidence, such as fossil growth rings, confirms that days were shorter in the distant past, approximately 22 hours long during the late Precambrian. This gradual deceleration further contributes to long-term stability of Earth's spin axis. Beyond Earth, the Moon's influence provides a case study for understanding other planetary systems. Planets without large moons may experience more chaotic axial tilts, leading to unpredictable climate. In contrast, systems with significant satellites show evidence of greater rotational stability. Observations of exoplanet systems support these models, demonstrating that satellite-induced stabilization is a general principle. You imagine Earth in its early history, rotating faster and tilting more erratically. Without the Moon, axial shifts might have been dramatic, altering climate, ocean circulation, and the development of life. The presence of the Moon imposes a gravitational constraint, producing a stable environment over geological timescales. Tidal forces contribute to stability beyond axial tilt. The Moon's gravitational pull raises tides in the oceans, creating bulges that continually adjust with Earth's rotation. These bulges interact with Earth's crust and mantle, generating friction that further influences rotation and axial orientation. The effect is small in a daily sense but accumulates over millions of years. The Moon also affects precession, the slow wobble of Earth's rotational axis. Precession cycles last roughly 26,000 years and subtly shift the orientation of the axis in space. The Moon's gravitational torque regulates the rate of precession, ensuring that these cycles remain gradual rather than chaotic. Observational data confirm that precession proceeds steadily, matching predicted values. You notice how these gravitational interactions are interconnected. Axial tilt, rotation rate, tidal bulges, and precession all respond to the Moon's presence. None are arbitrary. Each follows measurable laws of physics, producing patterns that are slow, predictable, and detectable through observation. Geological and astronomical records provide converging evidence. Satellite missions provide further verification. Laser measurements of Earth-Moon distance show small, gradual changes consistent with angular momentum transfer. Observations of Earth's rotational behavior, combined with climate proxies, confirm that the Moon has exerted a stabilizing influence throughout recorded history. Every line of evidence reinforces the same conclusion. You begin to see the Moon not as a passive companion, but as an active participant in Earth's long-term behavior. Its gravitational presence shapes conditions at planetary scale. Seasons remain consistent, climate cycles predictable, and the planet's spin axis steady. Stability emerges as a measurable consequence of physical law, not chance. Even small variations in tilt, precession, and rotation are predictable. Milankovitch cycles, tides, and slight changes in day length all occur within a stable framework. The Moon's role is subtle, invisible to casual observation, but undeniable when examined through precise measurement and modeling. You imagine looking back in time. Over billions of years, life and climate evolved under the Moon's stabilizing influence. While continents shifted and ice sheets advanced and retreated, the planet's axial tilt remained constrained. The Moon quietly ensured that seasonal patterns endured, providing a foundation for biological and environmental continuity. The connection between Earth and its Moon is thus reciprocal. Earth shapes the Moon through tidal locking, orbital motion, and gravitational influence. The Moon shapes Earth by regulating tilt, rotation, and climate patterns. Both bodies respond predictably to mutual forces, producing a long-term balance that can be measured and confirmed. You rest with the realization that what feels eternal in the night sky is the result of slow, methodical physical processes. The Moon's steady presence stabilizes a spinning planet beneath it, producing conditions that are slow, safe, and predictable. The system operates without drama, without sudden change, and without mystery, following the exact laws that govern motion across the universe. As you watch the Moon overhead, you sense that its influence extends beyond tides and visible phases. Gravity shapes time, tilt, and climate, quietly imposing stability on Earth. These patterns set the stage for understanding other worlds, where moons and planets interact in ways that mirror the familiar, measured behavior of our own system. You broaden your perspective, considering the Moon as one example in a larger cosmic family. Its motion, rotation, and tidal interaction are not unique. Other planets, especially the gas giants, host moons that exhibit the same gravitational principles, and their orbits provide a laboratory for understanding celestial mechanics at scale. Jupiter, with its massive gravitational pull, holds dozens of moons. The four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean satellites. Each exhibits behavior similar to Earth's moon, though on a more extreme scale. Their rotation periods are synchronized with their orbital periods, producing tidal locking just as Earth's moon does. You notice the effect immediately in spacecraft data. Missions such as Voyager and Galileo recorded precise positions, rotation rates, and orbital parameters. Io, for example, completes one rotation in the same time it takes to orbit Jupiter, always presenting the same hemisphere to the planet. Ganymede and Callisto show similar synchronous rotation. These patterns match theoretical predictions based on mass, distance, and tidal forces. Tidal locking arises naturally wherever gravitational forces act over long periods. The principle is universal. A body close enough to a massive primary, with sufficient internal flexibility to dissipate rotational energy, will eventually achieve synchronization. The Moon, Jupiter's satellites, and even moons around Saturn and Uranus all demonstrate this outcome. Saturn provides additional examples. Titan, Saturn's largest moon, is tidally locked, maintaining the same face toward its parent. Cassini observations measured surface rotation and orbital period, confirming this synchronization to remarkable precision. The principles are the same as for the Moon. Torque from tidal bulges slows rotation until equilibrium is reached. Larger moons show secondary effects similar to Earth's moon. Tidal heating is one example. Io's interior remains geologically active because of tidal stresses from Jupiter and the other Galilean moons. These stresses flex the moon's interior, producing heat, volcanism, and surface deformation. While Earth's moon is largely cooled, the same mechanism demonstrates the broader range of outcomes depending on orbital parameters and internal structure. You recognize that tidal locking is not limited to moons. Close-orbiting exoplanets experience the same physics. Many exoplanets detected around other stars, particularly hot Jupiters or small rocky worlds in tight orbits, are expected to become tidally locked to their host stars. Their rotation periods match their orbital periods, just as with moons in our solar system. Observational evidence confirms this. Thermal measurements and phase curves of exoplanets reveal that one side consistently faces the star, absorbing heat, while the opposite side remains cooler. Models incorporating tidal locking accurately predict surface temperatures and atmospheric circulation, validating the universality of the underlying physics. You notice that orbital resonances often accompany tidal locking. Jupiter's Galilean moons are in a Laplace resonance, where the orbital periods of Io, Europa, and Ganymede form a precise ratio. This resonance maintains stable orbital spacing and enhances tidal effects, illustrating how multiple bodies influence each other in predictable ways. Similar resonances are observed in other satellite systems. The Moon, while simpler, provides a foundation for understanding these interactions. Its tidally locked state, recession rate, and interaction with Earth's rotation serve as a benchmark. By studying a well-characterized case close to home, scientists refine models for distant, more complex systems. Measurement, observation, and theory combine to produce confident predictions for moons and planets alike. You consider that tidal effects also influence orbital evolution. The Moon moves away from Earth at a measurable rate, about 3.8 centimeters per year. Similar processes occur in Jupiter and Saturn systems. Moons can migrate outward, settle into stable resonances, or, in rare cases, spiral inward if tidal forces act differently. Observations of multiple systems confirm these principles are consistent. Exoplanets provide further confirmation. Systems with short-period planets exhibit synchronized rotation and predictable orbital patterns. Scientists measure light curves and radial velocities to infer rotation states and orbital distances. Results consistently align with predictions based on tidal theory. What the moon demonstrates locally becomes a template for interpreting distant worlds. The moon's orbit also offers lessons about axial tilt and precession. Just as the moon stabilizes Earth's tilt, large moons elsewhere can influence planetary obliquity. Simulations of exoplanet systems suggest that moons reduce extreme axial variations, producing climates that might be more stable and predictable. Understanding this effect relies directly on insights gained from our own Moon-Earth system. You notice that tidal locking, librations, and gravitational interactions form a continuum. The moon illustrates the outcome of these forces over billions of years. Jupiter and Saturn's moons extend the principle to multiple body systems and more extreme conditions. Exoplanets push the principle into entirely new regimes. Each case reinforces the universality of physical law. Observations of orbital dynamics, surface features, and thermal behavior all tie together. Synchronous rotation is verified by visual imaging, radar mapping, and infrared measurement. Tidal heating is inferred from surface activity. Orbital resonances are confirmed by timing signals. These data points converge to support the same fundamental conclusions derived from the moon. You appreciate that the moon's simplicity is an asset. Its single, well-understood tidal interaction provides a clean case study. In more complex systems, additional forces complicate analysis, but the core principles remain unchanged. Observations, models, and predictions align, showing that physics operates consistently across scale and distance. Even subtle phenomena such as libration or recession are measurable elsewhere. Spacecraft tracking, radar ranging, and precise timing reveal small wobbles, orbital migration, and rotational synchronization. These effects, minor on human timescales, are consistent with predictions made from Earth-Moon studies. Observation repeatedly confirms theory. You rest with the understanding that the moon is not an isolated curiosity. Its tidally locked motion, orbital stability, and long-term evolution exemplify physical principles that apply universally. What is visible from your night sky becomes a model for interpreting moons and planets throughout the cosmos. The moon's motion is steady, measurable, and predictable. Its orbit and rotation are part of a larger pattern of gravitational interaction that extends to other worlds. Observing its behavior teaches you how to expect similar outcomes in more distant systems. This insight quietly prepares your mind to consider how precise measurements can confirm even the smallest motions, bridging observation and theory with confidence. You focus on the moon as a target for exact measurement. While telescopes provide images and orbital data, lasers allow for precise distance calculations. The technique is straightforward in principle. Send a pulse of light to the moon and measure the time it takes to return. In practice, achieving accuracy requires careful preparation and specialized equipment. Astronauts from the Apollo missions installed retroreflectors on the lunar surface. These small arrays of corner-cube prisms reflect incoming light directly back toward its source. Unlike a mirror, which reflects light at a specific angle, a retroreflector returns light along the same path, even if the incoming beam arrives at an angle. This property makes them ideal for measuring distances across hundreds of thousands of kilometers. Once a retroreflector is in place, scientists on Earth aim a laser pulse at it. The pulse travels to the moon, strikes the reflector, and returns. By recording the round-trip time with extreme precision, the distance to the moon is calculated using the constant speed of light. The process is repeated hundreds or thousands of times to reduce measurement uncertainty. You notice that this method provides extraordinary accuracy. Distances can be determined within a few millimeters. Over the decades, repeated measurements have confirmed not only the moon's distance, but also its gradual recession from Earth, approximately 3.8 centimeters per year. This slow motion is consistent with tidal interaction models. Multiple reflectors across the lunar surface allow measurements from different angles. By comparing returns from various sites, scientists confirm that the moon maintains a stable orientation. Tiny variations in rotation are detectable, including small wobbles corresponding to librations. Laser ranging thus provides real-time confirmation of rotational stability predicted by theory. The technique also allows scientists to monitor long-term trends. By tracking the distance over decades, researchers observe the gradual outward migration of the moon's orbit. This observation matches predictions based on tidal dissipation in Earth's oceans. The moon's motion, while slow, is measurable and consistent, reinforcing confidence in physical models. Retroreflector experiments also improve understanding of Earth. Measurements refine knowledge of Earth's rotation rate, polar motion, and orbital parameters. Even slight variations in Earth's spin contribute to changes in measured distance. Data integration provides a precise, interconnected view of Earth-Moon dynamics. You imagine the setup. Observatories equipped with powerful lasers, detecting returning photons after a journey of over 300,000 kilometers. Each measurement requires timing accuracy to billionths of a second. Atmospheric interference and thermal effects must be accounted for. Yet the results are consistently reliable, showing the moon as a stable, predictable partner. The lunar surface itself participates silently in this experiment. The reflectors, protected by durable prisms, withstand temperature extremes and micrometeorite impacts. Their continued functionality over decades ensures a continuous stream of data, allowing incremental improvements in measurement precision year after year. Even slight variations in the moon's rotation are detectable. Longitudinal and latitudinal librations cause retroreflectors to move subtly relative to Earth-based observatories. By analyzing these shifts, scientists confirm predicted oscillations. Observational evidence aligns with theoretical expectations, strengthening understanding of tidal locking and rotational dynamics. You notice that laser ranging is not merely an abstract exercise. The technique has practical implications. Accurate knowledge of lunar distance supports spacecraft navigation, orbital modeling, and future mission planning. It also demonstrates how relatively simple physical principles, speed of light, reflection, and precise timing, can yield extraordinary insights when applied with care. In addition, measurements provide constraints on fundamental physics. The Earth-Moon system serves as a natural laboratory for testing gravitational theories. Observations from laser ranging experiments help verify aspects of general relativity, including how gravity propagates and influences motion over large distances. The moon thus contributes to understanding universal principles. Data from these experiments are collected continuously. Observatories around the world participate in routine measurements, sometimes as part of collaborative networks. The repetition over decades reduces errors and enhances reliability. Each pulse of light, returning faithfully from the lunar surface, adds to a growing record of orbital knowledge. You reflect on the scale of these observations. A photon leaves Earth, traverses space, reflects from a tiny prism on the moon, and returns. Despite this vast distance, precise instruments capture the return and convert it into meaningful data. The moon becomes a bridge between human precision and cosmic scale. Measurements also confirm rotational stability. Any sudden change in rotation would alter the timing of returns. Over decades, no unexpected shifts have been detected. This steadiness aligns with models of tidal locking and provides further evidence that the moon's spin remains synchronized with its orbit. You appreciate how simplicity and patience combine in this work. The experiment relies on fundamental physics, careful engineering, and repeated observation. It demonstrates that even subtle, slow processes like orbital recession or libration can be quantified and understood. Through laser ranging, the moon emerges as an exact, measurable object rather than a distant, unknowable presence. Its distance, orientation, and motion are all accessible through observation, confirming predictions of physics and providing a foundation for both practical and theoretical understanding. As you rest your focus on the moon, you sense the steady pulse of measurement across time. Night after night, photon by photon, the moon communicates its position and motion, revealing a system that is precise, predictable, and remarkably stable. This quiet exchange of light and calculation highlights the power of careful observation in understanding celestial mechanics and prepares you to integrate geometry, motion, and illumination into a unified view of the moon's appearance. You focus on the moon's changing appearance in the night sky. Its phases are not random or mysterious. They follow precise patterns determined by the relative positions of the Sun, Earth, and Moon. Each night, the angle of sunlight striking the Moon shifts slightly, altering the illuminated portion visible from your perspective on Earth. The cycle begins with the new moon, when the moon is positioned between Earth and the Sun. From your viewpoint, the sunlit side faces away, leaving the near side in darkness. Over successive nights, the moon moves along its orbit, and the sunlight angle gradually reveals more of the near side, producing a waxing crescent. This progression continues until the full moon, when the Earth lies between the Sun and Moon, and the near side is fully illuminated. Waning phases follow in reverse order. After the full moon, sunlight begins to illuminate less of the near side, producing a waning gibbous, then a last quarter, and finally a waning crescent. The cycle takes roughly 29.5 days, defined as a synodic month. The timing and sequence are consistent and measurable, verified through centuries of observation and calculation. You notice that the moon's changing position in the sky interacts with libration. The slight oscillations in rotation and tilt allow you to see small portions of the far side that would otherwise remain hidden. Over a month, the combination of orbital motion, axial tilt, and libration produces subtle variations in shape, edge features, and apparent orientation. Eclipses further demonstrate the predictability of the system. A lunar eclipse occurs when Earth passes directly between the Sun and Moon, casting a shadow across the lunar surface. The geometry of the orbits ensures that eclipses are not random events but occur at intervals determined by the alignment of nodes, points where the Moon's orbit crosses Earth's orbital plane. Solar eclipses operate on the same principle. When the Moon passes between Earth and the Sun, its shadow falls on part of Earth's surface. Precise measurements of orbital distances, angles, and motion allow astronomers to predict the timing and location of eclipses years in advance. Ancient records show early civilizations noticed these cycles, and modern instruments confirm them with exact precision. You realize that phases, eclipses, and libration all reflect the same underlying factors: the Moon's orbit, rotation, axial tilt, and relative position to the Sun and Earth. The visual changes are manifestations of geometric relationships combined with light, rather than intrinsic changes in the Moon itself. Every waxing and waning, every slight wobble, follows predictable physics. Observational data confirms the geometry repeatedly. Photographs taken over multiple months show consistent shapes and timings. Amateur astronomers tracking the Moon across nights observe the same sequence of phases and edge movements. Spacecraft images provide additional confirmation, capturing the Moon from multiple angles and distances, and revealing how illumination and perspective combine to produce the observed appearance. You notice that perspective also plays a role. The Moon's position in the sky varies with latitude and time of night. Observers in different locations on Earth may see the Moon slightly rotated relative to others, an effect amplified by diurnal libration. These differences are measurable and predictable, allowing careful observers to account for them when mapping surface features. The cycle of lunar phases is linked to the orbital motion in a straightforward way. As the Moon completes one orbit around Earth, the proportion of the near side illuminated by the Sun changes steadily. The progression is smooth, continuous, and accurately modeled with simple trigonometry and orbital mechanics. Deviations are minimal and occur only due to minor perturbations from the Sun and other planetary bodies. You consider that this predictability underlies both scientific observation and human experience. Calendars, agricultural planning, and cultural traditions historically relied on lunar phases. Modern science translates these patterns into precise timing for telescopes, spacecraft missions, and even lunar laser ranging experiments. Observation and calculation work together seamlessly. The Moon's surface features interact with changing illumination. Craters, mountains, and valleys cast shadows that shift with the Sun's angle. These shifts enhance visibility of topography, allowing detailed mapping from Earth-based telescopes. Subtle differences in brightness and shadow provide additional information about slope, composition, and surface roughness, reinforcing that apparent change is purely geometric and optical. Eclipse phenomena also highlight the three-dimensional arrangement of the system. The Earth-Moon-Sun configuration can be described mathematically, and observed shadows match calculations exactly. Partial, total, and penumbral eclipses occur at precise intervals and locations, confirming the alignment of orbital nodes, inclinations, and distances. You notice that the Moon's apparent size varies slightly due to changes in distance. Its orbit is elliptical, so perigee brings the Moon closer, making it appear slightly larger, and apogee moves it farther, making it appear smaller. This variation is subtle but measurable, contributing to the visual dynamics of eclipses and phases. The combination of phases, libration, eclipses, and apparent size illustrates a unified system. Each aspect can be predicted from the Moon's orbital parameters, rotation, and axial tilt. Calculations align with direct observation, demonstrating the harmony between theory and measurement. Nothing is left to chance. Each visual shift is accounted for by measurable motion. You also notice the Moon's motion relative to stars. Over nights, it progresses eastward against the background stars, approximately 13 degrees per day. This motion interacts with phases and libration to produce the complex but predictable patterns you see. Accurate modeling requires incorporating rotation, orbit, tilt, and perspective simultaneously. Observational consistency provides confidence. Telescopic records, spacecraft images, and laser-ranging data all confirm positions, timing, and angles. Amateur and professional astronomers alike reproduce the observations. The Moon's appearance is never uncertain. Apparent change is always interpretable through geometry, motion, and light. You begin to appreciate that the Moon's changing face is an integrated expression of multiple physical factors. Phases, edge wobble, tilt, orbit, eclipses, and distance interact smoothly. What you perceive as dynamic is, in fact, a steady, predictable system governed by gravitational laws and geometric principles. As you settle your attention, the Moon's motions appear calm and reliable. Its phases are gentle cycles, eclipses are orderly, and librations reveal just enough of the hidden hemisphere to enrich observation. Each shift corresponds to measurable parameters, allowing you to anticipate and understand every subtle change. The Moon's predictable motion quietly reinforces the consistency and order of celestial mechanics, preparing your mind to reflect on the broader patterns that govern the universe and the place of stable motion within it. You allow your mind to take a broader view, considering the Moon not only as an individual body but as part of a vast, interconnected system governed by the same laws everywhere. Its steady rotation, synchronized orbit, and gradual recession illustrate how physical principles operate reliably across time and space. Nothing about its behavior is arbitrary. Every motion is a consequence of measurable forces and conserved quantities. The Moon's tidal locking demonstrates how rotational energy interacts with gravitational forces. Over billions of years, the friction induced by tidal bulges in Earth and the Moon dissipates energy, gradually bringing rotation and orbit into harmony. This process is slow and predictable, confirming that systems naturally evolve toward equilibrium under consistent forces. Observational data, including laser ranging measurements and crater studies, validate these predictions. Axial tilt, precession, and libration are further examples of ordered motion. Each represents a response to gravity, orbital geometry, and angular momentum. You notice that small oscillations do not indicate chaos. They reflect the nuanced ways in which celestial bodies respond to multiple, overlapping forces. These subtle movements are measurable, repeatable, and entirely consistent with theory. The Moon's influence on Earth reinforces the principle that stability emerges from interaction. Its gravitational pull moderates axial tilt, contributing to long-term climate consistency. The exchange of angular momentum between Earth and the Moon lengthens Earth's day and gradually increases the Moon's distance. These processes, imperceptible on human timescales, accumulate over eons, producing predictable outcomes that are entirely explainable. You notice that this pattern repeats across the solar system. Jupiter and Saturn host numerous moons, many of which are tidally locked, occupy resonant orbits, and experience tidal heating. Observations confirm that gravitational interactions lead to stable configurations, just as with Earth and its Moon. Exoplanetary systems follow the same principles, showing that these laws are universal, not local. The moon's predictable motion also allows for precise measurement and modeling. Retroreflectors enable millimeter-level determination of distance, while long-term tracking confirms the slow outward drift. Astronomical calculations predict phases, eclipses, and librations with accuracy spanning centuries. The moon exemplifies how observation and theory align to produce a complete understanding of natural processes. You appreciate that apparent complexity is resolved through physical law. The shifting phases, subtle wobbles, and slow orbital changes are not signs of randomness. Each is a consequence of well-understood forces: gravity, inertia, energy conservation, and angular momentum. When measured carefully, every motion can be anticipated, reinforcing a sense of order and continuity. The moon also offers a perspective on time. These processes unfold slowly, but not infinitely. Orbital recession, tidal locking, and the evolution of surface features demonstrate the cumulative effect of small forces over vast spans. You perceive motion as gradual, measured, and stable, contrasting with the immediate, chaotic changes often observed in daily life. These slow patterns create a sense of calm continuity. Observing the moon encourages reflection on universality. Physical laws governing its behavior are identical to those operating elsewhere. Angular momentum, gravitational attraction, tidal dissipation, and orbital resonance apply to planets, moons, stars, and galaxies. The consistency across environments illustrates that the universe operates under reliable, intelligible principles. You notice how interconnected phenomena reinforce each other. The moon's steady orbit affects Earth's rotation, axial tilt, and tides. Earth's response influences the moon's distance and motion. Even small effects, when integrated over long periods, produce measurable results. Each component of the system communicates through physical law, resulting in a predictable and harmonious arrangement. The moon's phases, eclipses, and librations become examples of visual evidence that confirm theory. Observers can track illumination, edge movements, and orbital position, all aligning with calculations. The regularity of these cycles demonstrates that celestial mechanics can be understood, modeled, and anticipated without invoking mystery. Observation becomes a form of quiet reassurance. You also recognize the moon's surface as a chronicle of time. Craters, Maria, and Highlands record impacts, volcanism, and internal evolution. The preservation of these features reflects slow geological processes, emphasizing stability and endurance. The moon's exterior, like its motion, follows the laws of physics faithfully, offering insight into both its history and the mechanics of motion itself. From this perspective, the moon serves as a bridge between human observation and universal principles. Its measurable behavior allows you to grasp abstract concepts concretely. Angular momentum, tidal interaction, orbital resonance, and gravitational stabilization become comprehensible through direct observation and precise measurement, reinforcing confidence in the consistency of natural law. You notice that the moon, in all its motion, exemplifies balance. Forces act, energy is conserved, and interactions proceed predictably. Rotation, orbit, tilt, and distance are all maintained within narrow ranges over geological timescales. What appears to shift or change is simply a manifestation of calculable motion and light, never random or unexplained. The quiet order of the Earth-Moon system mirrors broader patterns in the solar system and beyond. Planets, moons, and stars all respond to the same underlying rules, producing systems that are stable yet dynamic. Motion is continuous but gentle, predictable yet varied, illustrating that stability does not imply stasis but a balanced flow of forces. You appreciate that your understanding does not diminish wonder. Recognizing the moon's motion as lawful does not make it less remarkable. Instead, comprehension provides a sense of connection to the universe. Its rhythms become observable, measurable, and relatable, offering comfort in the predictability of vast, slow cosmic processes. Finally, you reflect on motion itself. Every spin, orbit, and oscillation is part of a continuum governed by simple laws. Observing the moon allows you to perceive the subtlety of this motion, the interplay of forces, and the reliability of natural law. The universe, once abstract, appears intelligible, slow, and safe, inviting quiet contemplation of the patterns that extend far beyond what you can see. As you focus on the moon's steady course, you sense that its behavior exemplifies the fundamental principles that govern all celestial bodies. Rotation, orbit, and gravitational interaction combine to produce calm, measurable patterns. Understanding these motions allows you to observe the universe as a coherent system, where stability emerges naturally from physical law, providing a foundation for reflection on the vast, ordered cosmos that surrounds Earth.